Hello, and welcome to MME 3309, Electronic Material Science and Technology. Today, we are going to be talking about kinetic molecular theory. And why do we care about kinetic molecular theory? Well, kinetic molecular theory is where we get the ideal gas law, PV equals nRT. The book uses a notation N over NA in place of N, which is the number of moles. So don't be confused by that notation. So we start off with our explanation of kinetic molecular theory. We start off with a square container with sides A, and we have a molecule traveling in the x direction. It hits face A, bounces off face A, hits face B, bounces off face B, and then hits face A again. So the diagram's a little bit exaggerated, but we can conclude that the change in momentum is mostly in the x direction. So we can describe an equation or set up an equation to tell us the change in momentum. Delta P, that's little p. And I don't think you can read that. So momentum equals 2 times the mass of your molecule times v sub x. Okay, so the velocity in the x direction. Now, we also want to know how much time it took for that molecule to traverse these sides of the box. So we can say delta t. So the change in time is 2 times the distance of the length of that box over v sub x. So velocity in the x direction, because right now we're setting up this model that the momentum changed mostly in the x direction. So pressure, okay, is what we're interested here in the ideal gas law. Pressure is force over area. So if we're trying to understand the ideal gas law and how we get there from molecules hitting the side of the box, we want to know what the total force is, or what the force, an equation describing the force of the molecules hitting the side of the box. So that force is change momentum over change in time, which we've described above as 2mvx over 2a over v sub x. And let me rewrite that for your viewing pleasure. Which can then be rewritten as mass of a molecule times velocity of the molecule squared in the x direction over a. Okay, so we said pressure equals force over area. Okay, and so we're interested in the pressure exerted by n molecules on face A. Okay, so it's sum of all of the molecules traveling in that x direction. So P equals total force over area, which is A squared. So that equates to the summation of all the molecules traveling in the x direction. Don't get too hung up by the notation used in the book. The book doesn't use a summation sign. The book also kind of neglects to say in this part that or include the term for the number of molecules hitting face A. So you could describe this portion here as the sum n, so n molecules, with n equals 1 of x, mass, I guess you could factor out the m as well, but we won't at this point, xn. Okay, so don't get hung up on the notation. And so this is divided by a cubed, a cubed. Okay, so the force is mvx squared over a, pressure is force over area, area is defined by a squared. So when we want to calculate pressure, we get force over area, and since we have an A term or a term describing the length of the box, we end up cubing it, which gives us volume. Okay, so we're getting the V now. So we're getting a P, and we're getting the V from our PV equals nRT. And we can rewrite, since we're really kind of doing this, we can rewrite that equation. Okay, first we can factor out the M, as the book is doing. MV, M factored out, VX1 plus Vx2 dot 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 Vxn. Okay, and so then we rewrite the equation now as P equals 2 m n, the number of molecules. And so the book uses this notation with the bar to describe the mean velocity in the x direction over the volume. Okay, so now we're talking about just the x direction. So it turns out that the mean squared velocity in the x direction is equal to the mean squared velocity in the y direction, which is equal to the mean squared velocity in the z direction. So that means the mean velocity for the molecule, okay, because we want to take into account the molecules traveling in all directions, can be defined by this term, v squared, okay, and that equals the summation of the molecules traveling in all three directions. So this is given to us now that we can describe the mean velocity for a molecule, take into account all directions by simply multiplying the mean squared velocity in the x direction by 3. Okay, so that brings us to this equation. So this is a rewrite of the equation that we just talked about. So we'll thumb back. That bad boy is a rewrite of this equation. Okay, and so this is referred to as gas pressure in the kinetic theory. We're still not quite to the ideal gas law yet. We'll get to this guy in a second. Okay, so let me get to the next slide here. Okay, so we've talked about, we were just given this guy. I keep saying this guy. We were just given this equation. So pressure equals the number of molecules times mv squared, the mean squared velocity. This is taking into account all directions. We know that because then we have to divide it by 3 to make it equate to the other equation that we got this from. This happens to be equal to 1/3 times the density times velocity squared, but that's really incidental in the derivation of the ideal gas law. So we come now and then we can say PV equals 2/3 n, and that equals to 1/2 mv squared, the mean velocity squared. And so what we've really done is we've dissected this guy, okay? So we've dissected 1/2 mv squared, okay, to talk about kinetic energy. And that's why we care about this here now, but we'll talk a little bit more about this guy in a little bit. Okay, so we've really just dissected this equation here when we're talking about getting to the ideal gas law. Okay, and so okay, so we're almost there. So now we go back to this guy, the mean kinetic energy per atom. So that's described by 1/2 mv squared, and this is equal to 3/2 kT. Okay, so it's important to know that this relationship here is actually the Maxwell Boltzmann distribution law for molecular velocities. And if you can't read my chicken scratch, it's the Maxwell-Boltzmann law. Oh, there it is, distribution law for molecular velocities. So this law is actually mostly seen in this form, is 3 kT, oops, how embarrassing, 3 kT over m. Okay, so this is the Maxwell-Boltzmann distribution law for molecular velocities. Okay, so now we come here, we know that 1/2 mv squared is equal, okay, we know that 1/2 mv squared is equal to 3/2 kT. Okay, and I should have done a uppercase T, where this is the Boltzmann constant, which is the gas constant, the ideal gas constant, over Avogadro's number. Okay, so rearranging PV equals 2/3 N times 1/2 mv squared, okay, which is the equation that we've been deriving now, we can then get to PV equals N over NA RT, aka the ideal gas law. So that's how we get from a molecule hitting the side of the box to the ideal gas law.